Good afternoon. So let's continue with discussing a little bit more about symmetry. Yesterday's class we were actually looking at the basic symmetry operators such as rotation and then mirror, and then we saw a couple of them called as compound and combination operations, which involves rotation and a mirroring operation, or a rotation and a inversion operation. So very quickly, this is an example of the compound operation which involves a four-fold rotation and the inversion. If you look at this entire molecule, this entire thing, it involves neither 4 separately or the inversion separately, but a combination of both 4 and inversion is actually present, right? So that is represented in this particular manner with the order of rotation and a bar right on top of it. That means you have to perform the four-fold rotation and the inversion. So you can have similar versions of the other inversions also, like 3 bar, 6 bar, 2 bar, and so on and so forth. This one is another operation which is called 4 over m. This is read as 4 over m. Okay, so there is a four-fold rotation and then there is a mirror that's being present, right? So automatically, because of the presence of the four-fold rotation and the mirror, there is also an inversion which automatically appears here, right? So it is important to remember that sometimes a combination of these two operations can introduce additional symmetry elements in the molecule. The next one is 2 bar. It's very simple. You perform a two-fold rotation. So one is moved to this particular shaded atom where the atom or the atom does not exist, and then it is inverted here. Okay, this entire molecule possesses 2 bar, which is equivalent to a mirror plane. 2 bar is same as mirror, right? There's another compound operation 3 bar, which is also something that we looked at. You perform a 3-fold rotation and an inversion. 3-fold rotation and an inversion. A good way to actually generate these structures is to take a point, perform 3-fold rotation, inversion, and keep doing it until you are going to start repeating this structure. So there's a 3-fold rotation and an inversion. So one will actually go to 5, but it won't stay there, and then it will be inverted to point 2. So when you do this operation on this atom 1, it actually results in atom 2. When you perform the same operation on the just generated atom 2, it generates atom 3, right? Then you again do it on 3, it generates 4. Do it on 4 again, it generates 5. Do it on 5 again, it generates 6. But when you do it on 6 again, what does it generate? 1. It generates 1. So it will start repeating itself over and over again, right? So therefore this operation is 3 bar. In this case, there is a 3-fold rotation and an inversion center. Both are actually being present, right? Depending upon the kind of operations, sometimes you will have both, sometimes you will not have both. In 4 bar, you neither had 4, you did not have 1 bar. But in 3 bar, you are having a 3-fold rotation also present and the inversion center also being present. So this will actually give us some natural rules to remember when such when such things are happening. When you have 4 bar, you don't have 4 or 1 bar, but when you have 3 bar, you have both 3 and 1 bar. So basically it is with respect to whether the rotation is an odd number or an even number. Okay, so this is actually 6 bar. 6 bar is, what is the angle of rotation? When you talk about 6 bar, it is 360 over 6. So you have rotated by 60 degrees. So one is moved to this shaded portion here, shaded atom here, and then inverted. You get the atom number 6, and you keep doing this over and over again until you start regenerating the entire structure, right? So 6 bar happens to be similar to 3-fold rotation and a mirror plane, right? A 3-fold rotation and a mirror plane that is there perpendicular to it, right? If you look at this entire molecule, this atom 1 is reflected, atom 5 is reflected here, and atom 3 is reflected here. So you have both a 3-fold rotation and a mirror plane that is perpendicular to it. Okay, and it is important for us to know a few symbols that is associated with such such operations, right? They are called as improper rotations or improper reflections. Improper rotations means you rotate and then invert, rotate and then reflect, right? So this is the symbol for your 6 bar. This one is your symbol for 3 bar. So if you have something like that, it essentially means there is an axis passing through that point where this operation of 3 bar is being performed. Okay. Yes. 3 bar, which one? So in this manner you can have different combinations, right? You have 1, 2, 4, 1, 2, 3, 4 and 6 possible rotations. That is possible is the order of rotations that is possible is 1, 2, 3, 4 and 6, and associated with each of these rotations you can always have an inversion, or you can have a mirror plane that is perpendicular to it. But you will see that for certain rotations and mirroring you will probably generate an inversion center. For certain rotations and inversion you will probably be generating a mirror. Okay. So this is what happens is the roto-reflection axis is generally represented by S suffix S. So S1 means one fold rotation and a reflection, which is equal to a mirror, correct? One full rotation and a mirror that is perpendicular to it is nothing but a mirror, right? And it happens to be the same as 2-fold rotation and an inversion. Okay. S2 is nothing but 2-fold rotation and a mirror. Okay, this is nothing but so 2-fold rotation and a mirror generates a inversion center, right? 3-fold rotation and a mirror is nothing but a 6-fold rotation along with the inversion, right? So we saw here 3-fold rotation and a mirror is nothing but 6 bar. They are the same thing. A 4-fold rotation and a mirror. So whenever you have S suffix 4, it means a 4-fold rotation and a mirror, and that generates 4 bar, and S6 means 3 bar. Okay. So usually we have the following relationship. When X is odd, that means when the order of rotation is odd, S suffix X, that means when you rotate it by that amount and then reflect it, it is nothing but 2 times X bar. This entire thing is 2X the whole bar. Okay, that's what it means. So S3 will be 6 bar. Okay, S1 will be 2 bar, and X bar is equal to S2X, the same thing, right? X bar. So if you have 1 bar is nothing but S2, and if it is 6 bar is nothing but S3. So that is written in a slightly different way. When X is odd, S suffix X implies the presence of both X and M, and X bar implies the presence of both X and the inversion center when X is odd. Okay. These are some of the rules. You don't have to actually remember these rules, right? You can actually work it out and convince yourself that that turns out to be another symmetry element that we have already studied. Again, I would like to emphasize that are there any questions with this aspect? So when X is odd, okay, S suffix X, that means rotation by X and a mirroring, implies the presence of both X and M when X is odd. And when again X is odd, X bar implies, okay, the presence of both X and the inversion. That's what it means. Is it okay? Yeah. Once again, I would like to emphasize that all the operations that we have studied until now, the rotation, the inversion, mirror, all these other operations which we looked at, where you have a combination of them like rotation and reflection or rotation and inversion, they leave at least one point fixed, right? We discussed this in the last class also. Okay. So these are called as point symmetry operations. Called as point symmetry operations. Surprisingly, it is not required for us to study any other kind of symmetry operators. This is enough. Okay. Everything else can be built on top of this. So we would like to ask the questions whether there are other elements that leave no point fixed. Like the elements that we just studied now leave at least one point fixed. The inversion center, there is only one point which is fixed. In the mirror plane, you have all the points in the mirror fixed. Rotation axis means all the points on the rotation axis are fixed. But are there operations that we can think of which leave no point fixed? Translations, right? Translations. But but that is when you have translations, you are talking essentially about a infinitely large molecule. You are talking about a molecule or a system which is extending to infinity on either directions, right? On the x, y, z directions, or when you are talking about a plane in the x and the y directions. If you have a finite molecule, it is not possible for you to have symmetry operations which don't leave at least one point fixed. Okay, so there are of course more complicated methods of actually proving that, but we will not, that's beyond the scope of this course. So it is important for you to get convinced that we don't need to actually look at any other operations when we are talking about the symmetry of a finite molecule. Of course, when we have infinitely extending molecules, like for example a crystal which is extending to infinity, then it is extremely important for us to consider translations. Okay, we will do that also. So there are other operations like I just mentioned. These operations are essentially translations. There are two kinds of translations other than the basic translation that we just looked at, simply taking a unit cell and continuously moving it about the lattice vectors. In addition to that, we can have what is referred to as a screw rotation and a glide plane. Okay, screw rotation and a glide plane. Screw rotation involves rotating by a certain amount and then moving it up through a certain translation distance. Okay, that is also a symmetry operator. You will not be able to figure out, it will, if you perform those operations, you will be able to make the entire lattice overlap with itself. Okay. Then there is another one called as glide plane, where there is a reflection about a mirror, and then you will have to move it by a certain vector. Okay, this is called as a glide plane. This screw rotation axis that we just talked about involves rotation and then moving it along the axis of rotation by a certain amount. Okay, so when we talk about plane lattices, this symmetry element does not exist because we are only talking about these atoms or molecules distributed in the plane, right? If at all there is a screw rotation axis, it will rotate and it has to come outside the plane of the paper, but then that is no longer a plane lattice, right? So we want to talk about plane lattices first, and there the only additional translation symmetry operator that we need to learn is this thing called as the glide plane, okay, which involves a mirroring operation followed by translation. So it will look something like this. If you have a molecule like this, it will get mirrored like this and then it will be moved. Okay, there is no, this molecule doesn't exist, it is just an intermediate step that is being generated while I am creating this thing for explanation purposes, right? So we will start looking at plane lattice, the symmetry of the plane lattices and how we represent the symmetry, and talk about point groups and space groups that are associated with the plane lattice. Okay. So just to remind you, when we talked about the Bravais lattice in 3D, how many Bravais lattices were there? That is a space lattice. How many? So there were 14. Okay. It so happens that in 2D there are 5 plane lattices. We will look at the symmetry of the 5 plane lattices, and in the process of doing so, I will introduce what are referred to as the Hermann Maugin symbols that is used to represent the symmetry of the lattices, and hence also maybe 2D crystals. You will understand what exactly it means. Now, I told you that there is I've introduced terminology such as space group and point group, and a simple definition that I gave yesterday is that if you have a space group and from the space group you remove all symmetry operators that is associated with translation, you will get a point group, right? We will see what that means here. Okay. So, you have in 10 different point groups and 17 different plane groups possible. Okay, we will see some of them. I will give examples for some of them, and others you can actually work out and convince yourself that. So his question is, the differences between point group and space group. I will say the same definition here again, but it is going to be clear once we look at a couple of examples. Okay, so the definition is, or the way you can understand is, if you know the space group, suppose you know the space group, what is meant by knowing the space group? Say I know the Hermann Maugin symbol for a specific crystal, and that tells me what space group it is. Okay. From that, in that space group, there will be certain symmetry elements that is related to translation. If I pull out those translations, I will get a symbol which is basically the point group. Okay. This might not be very clear now, but having this definition in mind and looking at something that we are going to look at in the next few slides will make it very clear what this point group, what is the difference between this point group and the space group is. What you need to remember is this point group does not contain any translation based symmetry operators. It will contain only reflections, mirrors, reflection, rotation and reflection, rotation and inversion kind of operators. It will not contain the glide plane, to be precise, in 2D. That's what it means. Okay. So this is what we are going to look at. Again, I would like to re-emphasize that we are not looking at any motifs at this point. It is just the 5 plane Bravais lattice. They are just imaginary points. Okay, the mathematical construct. These symmetry elements are given in international or Hermann Maugin notation. Okay, the Hermann Maugin notation is what is generally used in material science and engineering, and there are other notations also possible, which is called as the Schoenflies notation, Schoenflies or Schoenflies. I don't know exactly how to say that, but this is a slightly different way of prescribing the symmetry elements for a given crystal. But Hermann Maugin symbol is very popular and is used extensively because it can be very easily to include the translation symmetry operators, like we will see in a bit. And once you look at the symbol of the Hermann Maugin symbol corresponding to a specific crystal, you will easily be able to identify with respect to what axis the various symmetry elements are placed. Okay. While I talk about symmetry like a mirror and rotation axis, right now, although you understand what it means to apply mirror using these simple structures, when I give you a complicated crystal, it may not be clear where the mirror is actually placed, where the rotation axis is actually existing. Okay. The Hermann Maugin symbol makes it very easy for you to identify these aspects, okay, because each symbol, each slot in the Hermann Maugin symbol will refer to a specific axis, and that axis will become clear as we talk about the various lattices. Okay. So this is the first plane Bravais lattice. Okay. So it is basically the this angle is arbitrary, some alpha, and this distance A and B is arbitrary, right? The only symmetry operation that this entire lattice will have extending in all the 2 directions is, what is it? Two-fold rotation, right? There is nothing else present in this lattice. There is just a two-fold rotation. And where are the two-fold rotation axes? Is there at each of the lattice points, and you can also identify ones right at the center and at the center of the unit cell itself. There are two-fold rotation axes passing through all these points. Okay. Now we just talked about symmetry. We just talked about the rotation. Okay, rotation alone. So the symmetry element 2 is present, right? Now if this were to actually a unit cell and it is covering the entire space, entire 2D space, how many lattice points are actually present per unit cell? Only one lattice point is present per unit cell. Therefore it is of what type? Primitive. Therefore we say that the plane group is P2. Okay. Now the definition or the distinction between space group and point group can be introduced. P is set primitive, that means there is one lattice point per unit cell. The second I say unit cell, it is referring to translation, it is referring to the fact that I am moving it in two-dimensional space, right? So this is somewhat referring to a translational symmetry, very plain translations. I am just moving it by this A in this direction and by B in the other direction, right? If I remove this, what is remaining? Just 2. So the point group is 2, the space group is P2. Okay, P2. This is the symmetry of the plane oblique Bravais lattice, which is the first plane Bravais lattice. This is called as the Hermann Maugin symbol. There is nothing, no other symmetry element that is actually present here. What about this one? This is actually the rectangular primitive lattice. Okay, this angle is 90 degree. Again, this is any arbitrary distance A. This is any arbitrary distance B. Okay. What are the symmetry elements that is actually present here? In terms of first, let us look at rotation. Always you look at rotation. That is the first step in identifying the symmetry elements. What are the symmetry elements present here? There is a twofold rotation. Okay, there is a twofold rotation present. Right. Now, in addition to that, there is something. What are they? There are two mirrors. There is a mirror like this, with its normal being the a-axis, right? This is a mirror. The red color one that is right here is a mirror, and it has a normal, right? So the second slot here corresponds to M and refers to the first non-equivalent axis which we may talk about, which is basically 1, 0. That is referring to the normal of the mirror. Now there is another non-equivalent direction in this case, which is the B, right? There is also a mirror perpendicular to the B axis, or with B axis as its normal. So there is also another mirror, and this refers to the next non-equivalent axis or non-equivalent direction, to be precise. So 2 mm, is this still primitive? It is primitive. However, 2 mm would be the point group, but if I put a P here, it refers to the space group. Okay, it refers to the space group. So when you see 2, automatically you should, when you see a 2 and a m, okay, or a 2 and a m, you will automatically be reminded of a rectangle. You will automatically be reminded of a rectangle. Okay, you will see that it will, after some time, you will automatically be recognizing what unit cell should be there. Once you look at this Hermann Maugin symbol, it will become a little bit obvious. Okay, the next one, the Bravais lattice, the next Bravais lattice is the rectangular centered. So there is a lattice point right in the middle. Now before we do that, how many of you think that there is a, there should also be a mirror like that? There is no mirror like that. Okay, generally there is a tendency to think there is a mirror like that, but there are no mirrors that way. If there were mirrors that way, this, what would happen if you put a mirror like this? This would look like this, right? It would reflect that way. So there are no mirrors. Rectangular centered, again there is a lattice point that is present right here. There is another lattice point, is a centered cell. Okay. Again, what are the symmetry elements that are present? There is a two-fold rotation, there is a mirror, and there are mirrors perpendicular to each other. The first slot refers to M and with its normal being 1 0, the second one being 0 1. However, this is centered. That means what is that? There is actually, you can actually think about a mirror that's here, okay, a mirror that's here, this lattice point being reflected about this lattice point being reflected about this mirror and being moved half the lattice distance. So this is actually a special glide plane per se, but it is moved exactly to the center, so we call it centered lattice and we put a C there. The point group of P2 mm and C2 mm is, what is it? 2 mm. You just remove the symbols which correspond to translation operations, right? What you will be able to identify obviously is the 4. That means if you rotate it by 90 degrees, you are able to make these atoms or these lattice points coincide with each other, and the lattice is simply indistinguishable from the thing that you started off with. What does this mean? This means it is making this A and this B the same. It is making this A and this B equivalent, correct? Right. In the previous case, in the rectangle, this and this was not equivalent. So we had 2 slots, one for this and the other for this. In the fourfold, when you are talking about the square primitive lattice, you obviously have a 4-fold rotation, and the next slot is a mirror with the normal as A, but there is no real distinction between A or B. So this mirror that may be present is the equivalent directions, either A or B. We can't like really distinguish between them because of the presence of the 4-fold rotation. Okay. The next non-equivalent axis or direction that is present here are these diagonals. So there are also mirrors above the diagonals, or the normals of the mirrors is the other diagonal. For example, the normal of this mirror is this diagonal, and the normal of this mirror is basically this diagonal. So there are mirrors, right? So the next non-equivalent axis is basically your 1 1 or 1 bar 1 directions. So if you have studied your basic material science and engineering, you might be comfortable with symbols such as these. If not, please refer to some basic material science book and you will follow what these directions mean. Okay. So when you look at 4, okay, when you look at M and another M, you will automatically, when it is a plane lattice, you will automatically be convinced that the unit cell that you have to use is a square, right? Automatically, when you see a 2 M and M, you will automatically be convinced that the unit cell that you have to use is a rectangle. When you see 2 and nothing else, you will know that the only thing that you can work with is this oblique parallelogram, right? So these symbols will automatically tell you, if I am giving you the space group of some complicated crystal structure, these symbols automatically tell you what unit cell is probably appropriate for you to construct this entire crystal, just by looking at this carefully. In 3D it becomes a little bit more complicated because you have certain other things coming in, but this is the basic idea. Finally, we have what is referred to as the hexagonal primitive Bravais lattice. Again, this is a little bit more involved. So you have, what is the symmetry operator that you can think of as far as the rotation is concerned? 6. There is a 6-fold rotation, right? There is a 6-fold rotation, right? 6-fold rotation means by 60 degrees, So if I am rotating by 60 degrees, there are certain things happen. When I rotate by 90 degrees, it made A and B the same, right? When I rotate by 60 degrees, it makes this one, this one all the same, right? It makes it the same because you are able to make them all that is what essentially the symmetry property means, right? So you have 6. In addition to that, you have mirrors, which you can easily notice. There are mirrors with normals as the A and the B axis, right? There are mirrors with the normal as A, B, or any equivalent AB axis, right? So the next M corresponds to the mirrors with normal as the A, normal as the B, or normal as any equivalent to A and B. So basically these are the mirrors. This one, because that has a normal A, and this one that has a normal B, and this one that has this one as a normal, and you also have, this is the same, right? These things are the same. So let us and then in addition, okay, let me complete this and let me show you how this looks in a little bit more detail and how to represent the directions for the hexagonal primitive in a little bit more carefully. The next, so this is basically a set of all these directions, right? These are the normals. So you are talking when you're talking about this mirror here, you're talking about the mirror which has normal as this A. So what would be this direction? Material science students, can you tell me what would be this direction? Maybe in the 3-index system. 1, 0, 0, right? And this one is 0, 1, 0, right? However, I mean, just a quick recap. However, this, I told you that this direction is also equal to this direction, these two directions. There is no difference. What is this direction in the 3-index system? 1, 1, 0. This corresponds to the C axis, right? This corresponds to the C. The problem with this hexagonal system is equivalent directions, although the directions are equivalent, the kind of indices that are appearing here are different. So 1, 0, 0, 0, 1, 0, you have 1, 0 and 0. Here also you have 0, 1, 0. But however, for this direction you have 1, 1 and 0. So the same equivalent directions don't have the same set of all the indices. Consequently, we have to resort to what is referred to as a 4-index system in order to address this problem. And if you do that using specific formula which you might have studied, you will make sure that all the equivalent directions have the same set of all the 4 indices. Okay, so this M, so we will do that in a little bit. This M corresponds to these axes. So I will say 1, 0, 0 in the 3-index system, but you will have to convert it into the 4-index system to indeed convince yourself that they are having the same set of indices. And the next M are the mirrors which have the bisectors of these A, B and C as the normals. So this one, for example, this one, okay, as the normals. That means the B, the A and the C axis themselves are the mirrors. Okay, so this is the other set of axes. So you can talk about them as 2, 1 or equivalent. 2, 1, 1 bar 1, 1 bar 1, 2 bar directions are all this mirror basically refers to that. So 6 mm is the point group associated with the hexagonal primitive, and when I put a P, it basically becomes the corresponding space group. Okay, space group. Right now we have, again to emphasize, right now at each of the lattice points, what is there? An imaginary point. In 2D, that point is having what? If you assume that point to be a motif, it is having all the symmetry possible, right? It is most symmetric motif that is possible in 2D. In 3D, it would be a sphere. Okay. So now let us just take a quick detour and look at these symmetry elements. I want you to know that. So we have this to be A and this to be B. Okay. And in the 3 index system, this is actually what? This is actually 1 0 0, and in the 3 index system, this direction is actually 0 1 0, and let us take another equivalent direction, and this one happens to be something like 1 1 0, right? 3 index. So if you know the indices in the 3 index system, so this we mark this as u prime, v prime and t prime. Okay, in the 3 index system, if you know u prime, v prime and t prime, then in the 4 index system you can find out the corresponding u, v and t using simple expressions like this. I think this also is probably there in your now this will give you a 4 index system u, v, w and t, and you can convince yourself that the set of numbers that appear here for the directions will be the same for all equivalent directions. So let us take for example the direction for A. The direction for A becomes what? 1 over 3 2 minus 0, which is equal to 2 by 3, and this one is 1 over 3 minus 1 bar over 3, and this one is minus of this plus this, which is 1 over 3, and t equal to t bar, which is 0 in this case because we are looking at plane lattices. Consequently, the direction here is 2 1 bar 1 bar 0. Is that right? Based on at least this formula should be right? 2 times u prime minus 0, which is 2 by 3 minus 1 by 3, 2 times this v prime minus u, which is 1, which you get minus 1 by 3 or 1 bar over 3, and w is minus of u plus v. So 2 minus 1 over 3, so you get minus 1 over 3. So if you write it down, you get 2 1 bar 0. So the set of indices involves 2, a 1, 1 and a 0. Now take a look at this one. So if you take a look at this one, what happens here? You should take this 1, it becomes 1 over 3, 2 minus 1, so you get 1 over 3. The second one is 1 by 3 times 2 minus 1, which is again 1 over 3. Add them up and put a minus sign, so you get 2 bar over 3 and 0. So this is 1 1 2 bar 0. So in a 4 index system, what's wrong with this? In a 4 index system, there is this direction is represented as 1 1 2 bar 0. In the 4 index system, this is represented as 2 1 bar 0. The same numbers are appearing in equivalent directions. That is why in the hexagonal system, the 4 index system is actually used. Okay. It should not be very hard for you to find out the directions in the 4 index and in the 3 index system for this equivalent axis, which is called the this is normally called A1, this is normally called A2, and this is normally called A3. And of course you can use any set, it doesn't matter. Okay. So the first set of mirror planes are the ones which have these equivalent axes as the normals. So that means it is these are the planes, these are the mirrors, these are the mirrors. Okay. and of course these are the mirrors. You will see that that mirror exists, right, if you take a look at it carefully. So the mirrors that I am talking about are these, which have the equivalent A, B, C as the normals. The next set of mirrors, which is referring to the third slot in the Hermann Maugin symbols, are the ones which have the bisectors of these equivalent axes as the normals. So basically the A, B and C lines themselves are the mirrors. That is what this refers to. So for the hexagonal primitive, this point group will be 6 M M and the corresponding space group will be P 6 mm, indicating the presence of a translation. Okay. So this 4 index and 2 index system can be a little bit confusing, but if you work it out carefully using these formulas that I have mentioned in this slide, it should not be too hard. Okay. Are there any quick clarifications before I go on to the next topic? A. The bisector mirror is not equivalent. The bisectors are normals to another set of mirrors, and the normals are nothing but going to be parallel to this, no, because this is a normal to this, right. So I mean that the mirror is right there over A, B and C themselves. It will be there. So if you take a look at this, so there is a mirror right here, right. This point is going here, this point is going here, and there is going to be a mirror, so perpendicular to this, there is a mirror right here. This is a mirror, but it is not the same as the mirror that is perpendicular to this. It's a different mirror. It's a different mirror. They are not equivalent. Okay. Yes. His question was, does it matter really what we call as A, B and C? So this is A, this is B and this is C, or A1, B, A2 and A3 in my in the example that I have taken. But I could have as well taken this as A1, this as A2 and this as A3, and it would be exactly the same. They are all equivalent. So these are the space groups, and from that we introduce some point groups just from looking at the Bravais lattices. Okay. Yeah, this is something that I already did. So we removed once you remove the elements, translation elements, you will automatically get what is referred to as the point group. Okay, we already did this, so I don't want to repeat this. So now, instead of a point at the Bravais lattice, okay, instead of the point at the Bravais lattice, I have a motif with some arbitrary symmetry. Okay. Then how many distinct patterns can actually be generated by applying only the symmetry elements, that is the rotation 1, 2, 3, 4, 6 and the mirror. So it happens that it's 10. Okay, it happens to be 10. So a useful exercise would be to find out the point group of a given pattern in 2D first and see if we can write down its point group. Okay. So like a molecule, I have given you a benzene molecule and I am asking you to identify its symmetry. The benzene molecule is not yet placed in any lattice. Once I place it in a lattice, the entire symmetry of the lattice is what we need to take into account, which will be different from the symmetry of the benzene, okay, or any molecule that I place. Right now I want to do at least 1 or 2 examples, maybe a little bit more, to see if we can with whatever we have learned, to see if we can identify the symmetry elements that is actually present in a given pattern. So what is this? What symmetry elements are present here? 6-fold symmetry. Once I talk about 6-fold symmetry, I should look for mirror planes. Where should I look for mirror planes? The first mirror plane I should look for is the one that is having the equivalent axis as the normals, right? These are the equivalent axes, obviously. So, do we have mirror planes which have normals as the A, B and the C axis? Yes, right? So, I shall write here M. Now, do we have mirror planes with the normals as the bisectors of these axes? This one, is that a mirror plane? Yes. Is this a mirror plane? Yes, right? All the there are, so basically is this a mirror plane? Yes. So, there are mirror planes here as well. So, the point group of this entire pattern is 6 mm. But this is a point group of the motif of this pattern, this single pattern. This is, previously we discussed the point group and the space group associated with the hexagonal Bravais lattice itself. P 6 mm means it is a primitive lattice. It is actually repeating in two directions. Here I am just talking about point group. I am not saying anything about its repetition yet. I am talking only about the symmetry associated with the molecule that looks like this. Okay. So, this is 6 mm. These are various symmetry elements. We will do one more before the, what about this one? Threefold rotation. Threefold rotation also can be treated as the sixfold rotation, because it also will have, you can talk about these axes. Okay. There is only the sixfold rotation will make this one and this one equivalent. The threefold rotation only makes this one and this one equivalent. Okay. There is a threefold rotation. Continue to look for similar mirrors. Is there a mirror perpendicular to the A, B and C here in this pattern? No, it is not there, right? So, in that slot I put a 1, which means the only symmetry that may be present there is just 1. There is nothing there. The next slot in the Hermann Maugin symbol refers to bisectors. So, the A, B and C themselves, is it there? Yes, right. So, there is a 3, 1 M. The point group of this pattern is 3, 1 M. So, you can actually systematically, based on the first rotation itself, identify what directions you have to look at for the mirrors, what unit cell you have to use and all that by just looking at this Hermann Maugin symbol. Okay.